Welcome back, everybody. We're going to do another dynamics problem, and it's going to be concerning the idea of the work energy principle. So the problem states a spring is used to stop a 50 kilogram package, which is moving down a 20-degree incline. The spring has a constant of 30 kilonewtons per meter and is held by a cable so that it is initially compressed 50 millimeters. If the velocity of the package when it is 8 meters from the spring is 2 meters per second, and neglecting friction, determine the maximum additional deformation of the spring and bringing the package to rest. So as I stated earlier, we're going to use the idea of work and energy to solve this problem. And the first thing we're going to do is actually define the initial and final states of the spring as well as the package. In the problem, it said the spring is already compressed 50 millimeters. So that means it's already compressed 50 millimeters from the equilibrium state. So that's what I'm going to do first. Define the equilibrium state for the spring. So that's going to be somewhere along here. So this is going to be the equilibrium line. So if the spring wasn't compressed, this is how far it would be up the incline, being not compressed. So I'm going to use the middle of the plate. We're going to ignore the width of the plate. And we're going to define this length, the initial compressed length of the spring, going to be 50 millimeters, or as I defined earlier, as S1. So later on, when the package hits the spring is going to compress even further down the incline, and that's going to be our final state. So I'm going to define our final state somewhere around here. It doesn't really matter. It's just a visual representation of where the spring is going to be when the package comes to rest. So we can define this other deformation as S2. So this right here is going to be the initial state of the spring, and this is going to be the final state of the spring. Now we have to do the same thing for the package. So the package itself has kinetic energy as well as potential energy. So the first thing we're going to define is the potential energy. So we're going to define our zero potential right when the box reaches its final state, which is going to be along this purple dashed line. So it's going to have zero potential along this line. And when I say zero potential, I mean zero potential in terms of gravity. So we could define the initial position as the state that's drawn right here for the package. So I'm going to use this point and draw a vertical line downward, and that's going to define our initial potential energy in terms of gravity. So we could define this height as h. So this is going to be the initial state of the box, and then the final state of the box is going to be the same as the final state of the spring. And just to recognize that this is going to be a right angle, so we can actually define h in terms of the length d and this extra length, which we'll call S2, or which is already called S2. So by using that triangle, we could define h in terms of d and S2, which will be used later to define S2, which is what we're looking for. So we could use this right triangle to define h in terms of d and S2. So now that we have that, we just have to define our work energy equation. So we're going to define the initial kinetic energy of the box. So that's going to be KE1 plus the potential energy of the spring, which is initially compressed. So that's going to be PES1. And then the gravitational potential energy of the box. So that's going to be PEG1. And then any work being done by external or non-conservative forces. So that's going to be W. And that's going to equal the final kinetic energy of the box, plus the final potential energy of the spring, plus the final potential energy due to gravity of the package. So now we can start canceling out some terms because some of these terms do not exist in the problem. So the one thing that does exist is that the box does have kinetic energy because it is moving at some velocity initially, which is 2 meters per second. It does have some potential energy as well, which is due to gravity because it has a height h at state 1, which is above the zero potential line. And the spring also has an initial kinetic energy because it is initially compressed by 50 millimeters. However, there is no work being done on the system or onto the box or the spring, so we could say that there is no work being done, and that's because there's no frictional forces or no non-conservative forces being acted on the system. So for the kinetic energy in the final state, it's going to be 0 because the package is coming to rest. So we could say that is going to be 0. And if the package is coming to rest, that also implies that the spring is also at rest as well. There is going to be some potential energy due to the spring because, again, the spring is going to be compressed a distance of S1 plus S2, which is a displacement from the equilibrium state. So when the box reaches its final state, the spring is going to contain some potential energy because it's still being compressed. And then the potential energy due to gravity at the final state is going to be 0, and that's because the box is going to be right here, which is directly in line with the 0 potential line. And if you're wondering why we're not concerned with the potential of the spring plate, that's because we're assuming that the mass of the spring's plate is going to be negligible, meaning it's practically 0. And also that is signified by the problem because it doesn't state that the spring has any type of mass. So this is going to be the equation that we're going to use. So we can just start plugging in our values for these energies. So we're going to have initial kinetic energy, which is 1/2 mv0 squared, plus mgh, and h is defined by this variable right here, so this is going to be d plus s2 times the sine of theta. We're also going to have potential energy of the spring, which is going to be plus 1/2 k s1 squared, and that's going to equal the potential energy of the spring in the second state, so that's going to be 1/2 k s1 plus s2 all squared. And again, this part of the equation is the displacement of the spring from equilibrium. So we can see that the displacement is going from here to here. And that is it for our equation. So our goal in this problem is to find S2, or in other words, the additional deformation of the spring right when the package comes to rest. So what I'm going to do now is actually distribute this part, the displacement of the spring, and rearrange the equation a little bit, so that we get in a quadratic equation. So to quickly recap of what I just did, all I did was multiply this part out, which got this part right here. And then from there, I just simplified here and collected like terms and moved everything to the left side so that I get an equation that is set equal to 0. And the reason why I did this is because we can actually solve this problem by using the quadratic formula. And we recognize this because we could create a quadratic equation by having S2 as the variable. So to make this easier to see, what I'm going to do is define some new variables or constants based on this equation. So I'm going to say let alpha equal 1/2 k, and that's just this coefficient right here. This is going to equal 15,000. And then we're going to let beta equal ks1 minus mg sine of theta. And that's just this constant right here. And that's going to equal 1332.23912. I don't know why I'm being so precise in this problem. So, and then we're going to let epsilon equal negative mgd sine theta minus 1/2 mv0 squared. And that's going to equal negative 1442.087. So the reason why I did this is so that we could see that this is actually a quadratic equation, because it looks pretty complicated with all these different variables. So we could actually rewrite this equation now in terms of these constants. So we can say that this is going to equal alpha s2 squared plus beta s2 plus epsilon, and that's going to equal 0. So now we could actually use the quadratic formula to actually solve this problem. So we could say that S2 equals negative beta plus or minus the square root of beta squared minus 4 alpha epsilon divided by 2 alpha. So after plugging all these numbers into your calculator, you actually get two different values due to this plus or minus here. And you get S2 equal 0.268 meters, and you also get negative 0.358 meters. And the reason why is because this is a quadratic equation, so when you're solving this equation, you get something that looks like this. So what you're really doing is finding what values of S2 satisfy this equation when it touches the horizontal axis or when the equation equals 0. So you're finding these 2 points right here. So that's why you get a negative value as well as a positive value. So when you get this negative value, it has no physical meaning. So that's why we just assume that this is going to be the correct answer. This is going to be the physical answer that makes sense. So the true answer is going to be this right here, 0.268 meters. So the additional deformation of the spring is going to be around 270 millimeters. So I'm going to quickly recap of what we just did. So the first thing we did was actually define the initial and final states of the spring. So that is basically how much the spring has stretched from the equilibrium state. And the problem said it was compressed initially by 50 millimeters, so we recognize that. So the initial state is defined of the spring as this purple dashed line right here. And then from there, we define the final state, which is going to be when the box comes to rest and compresses the spring a little bit further, and that's going to define by S2, and this is the value we're actually looking for. So the final state is going to be defined by this dashed line of the spring. Next, we define the initial state, which is going to be what is drawn right here of the package, and it's going to be pushed down this incline and reach this final state, which is going to be the same final state of the spring, and we define that also to be the zero potential line for gravity. So then we used our work energy equation and figure out that there's no external forces such as friction being acted upon the system, so we could say that the work being done onto the system is going to be 0, and we recognize that the kinetic energy is going to be 0 at the final state, and that's because the package is coming to rest. And we also said that the final potential is going to be 0 because we defined our zero potential line right where the final state starts and ends simultaneously. And then we just use this equation and plug in the known equations for kinetic energy, potential energy of springs, and potential energies due to gravity. And then we also define this relationship between H and D and S2. So from there, we plug in those equations and simplify this by multiplying this part out into this. And then we moved everything from one side to the other so that we get the equation set equal to 0. And that's because we're trying to make this into a quadratic equation. To make this look more like a quadratic equation, I defined these variables in terms of other constants such as alpha, beta, and epsilon, and we rewrote the equation in terms of this. And then to find S2, all we did was use the quadratic formula and plugged in the values and plugged it into our calculators to get two different values for S2. So we got one value that was positive and one value that was negative, and that's simply because we have a quadratic equation or a parabola that passes the horizontal axis at two different points. So that's why we get two different values for S2. Although the negative value doesn't make any physical sense because we know that the spring is going to be compressed later on in this direction, so we can't have a negative direction, meaning when the box moves towards the plate, it actually uncompresses the spring, so the spring goes upward. So that's basically what this value is saying, which we know that doesn't happen. So we can say that the actual deformation or the actual extra deformation of the spring is going to be 268 millimeters. So hopefully this helped you. This will be the end for energy problems in this playlist. There'll be more energy problems, I'm sure, in my other playlist called More Dynamics Problems, so be sure to check that out for extra practice. With that being said, I'll see you in the next video.